Nothing like starting Saturday morning with a big pile of boxes. YixEnergy has sent me the batteries, case, and stand for a DIY 48-volt home battery. And this one has some really unique features. I'm looking forward to putting it together and doing some testing. Welcome back to Projects with Everyday Dave. Let's get started. This base is a beast. Just amazingly smooth, robust casters. A box frame. These guys are not messing around. Wow. Has some little feet. Following these notches. I am liking this setup. Has some latches here. And then there's latches on the next battery, so you can just stack these up. That's pretty nice. These are nice batteries. 314 amp hour batteries. They have the double mount. I've actually already run a test on this, and they exceed their rated capacity. So I'm looking forward to building this battery. It's going to be one of the best ones yet. Whew, that's like a little mini workout. These are not light. We've got our 16 cells. We've got our case. Let's open it up and put it together. All of the bus bars, spacers, insulators, wiring, everything is contained inside the box. I need to take these bars out of the way so we can get all the components out, and we'll have to take the face off. They're providing EVA foam to put between each of the batteries. Allows you to adjust the space for compression. EVA foam for the top PCB boards. All the insulators. And the rest of the components. Nice. Flexible bus bars. Happy about that. All the screws for attaching the batteries. And look at that. This is new for a DIY kit. This is a fire suppressor. Now that is exciting. Some covers for the terminals, wiring, communications cables, zip ties, everything we need to put it together. I need to pop the front off so we can get to the compression plate and get the batteries put in. Looks like I have to actually detach this negative bus bar and a couple of cables in order to get this panel off. All right, there we go, got the face off. Now you can see the BMS mounted right to the back of this plate. And I don't think we have to take that off, we'll just remove the pressure plate. Very long bolts for the compression plate. There we go, BMS is removed. Compression plate comes with it. Case is empty. Time to build. Before I put the batteries in, I need to make sure that they're all the same voltage. So we'll check that real quick. 29, 29. Perfect. They're all at 3.29. Let's put them in. The structural integrity in this case is really nice. Very solid construction, solid frame all the way around the batteries. This is really well built. You can see the side has some box channel, the back. It's all framed nicely. Frame down the center to hold the compression plate. Really nice. The first task is to install the insulators. That's pretty nice. Some little sticky tape on the back of it here so it'll stick to the side. I've really thought of a lot. Really nice details about this case. First time I've seen built-in sticky tape. There's all the sides nicely taped in place. Protect the ends. All right, now we can put the batteries in. I've lined all the cells up here in the order they go in, and I'll put it up on the screen here for reference. The banks will be exactly the same, and every cell alternates, plus minus as we go down. We're supposed to put this EVA foam in between each one by sticking it to the cells. I'm not going to stick it on to start with because I want to make sure that the total stack up is appropriate. The reason they can both be identical is the back two rows are connected. So first put in a cell. Piece of EVA foam, and just repeat that process all the way up for both sides. Be very gentle with the cells. You don't want to nick them or scratch them. And it looks like there's actually a little bit of margin there. We'll see how that plate sits in on the end. I think there's some extra foam. We can space it out if we need to. Now at the end, I'll put in the last piece of foam and our insulators and see how the spacing comes out. Looks really close. Just a very slight gap there. There's 2 more pieces of foam. I think I should have started with a piece of foam at the very end, so I'll go ahead and slide those in the end. And I think that'll be just about perfect. 1 piece of foam at the beginning, 1 piece of foam between each cell, and 1 piece of foam at the end. Insulator at each end. Gives us just a very tiny little gap to compress, and that will hold them perfectly. I've shoved all the cells to the outside so that they're in perfect alignment. Now we can go ahead and tighten up our compression plate bolts. Snug right up to the plate, no gap, the cells are reasonably tight. I think we're good to go there. These boards will both capture the battery and do all the connection leads for battery voltage sensing for the BMS. We just need to put a piece of EVA foam on the back side here where it touches the cells, and there's an opening in the middle to clear the vent ports on the batteries. When you put these in, make sure you get the right board in the right place. A board is on the right, B board is on the left. With all the batteries in place, things start to get a little bit more dangerous. It's a good idea to start using insulated screwdrivers, maybe some rubber gloves. You can put some Kapton tape over things that you don't want to touch. You can even cover half the cells with a piece of cardboard or something, some rubber, so that you don't accidentally contact across those cells. Doing so could result in some significant energy release. So first I'm going to go ahead and secure these PCB boards. Time to install these beautiful flexible double hole bus bars. This is just 1 battery in series, and this is the plus and minus terminal. So all we have to do is connect them in a row. I'm going to leave out the bus bar that connects the 2 halves until the very end. That way I have half the voltage I'm working with in case I accidentally touch something I don't want to. I've temp set the inner bolts on all of the bus bars. Now I can connect the sensor wires to the remaining open locations. That way we always have 1 connection that isn't shared with a sensor wire. And some of these wires, the shrink tube is just a little too far up around the ring, so I'm gonna have to cut it back a little bit so it doesn't get sandwiched between the flange of the bolt head when I torque it down. It's another reason why I like to have a separate mount for the sensor wires. If for some reason you do get a little insulation under there, you're not compromising the integrity of the entire joint because you have 2 mounts that are completely secure with no interfering insulation. But it's easy to fix. We'll just trim it back a little bit. And it looks like there's quite a few of them that are just a little bit too tight, and you can tell because you put the bolt through and it covers past the insulation. Alright, I had to go around and trim the shrink tube back on every single sensor so that it wouldn't be trapped under my nuts and preventing proper contact. So now that that's fixed, we can go ahead and temp set all of our sensor wires. It's pretty hard to mess it up. They pretty much come out exactly where they have to be. You just bear in mind that you have to be able to check the voltage across every cell. So you have a sensor wire here and here, and a sensor wire here and here, and a sensor wire here and here. Basically, you're able to check the voltage of every individual cell so that it can be properly load balanced. And this has a 2-amp balancer, so it can actually take energy from one cell and move it to another. With all the sensors set and the main terminal put in position, I'm going to go ahead and torque all of those down so I don't have to come back to them. And if you're doing a professional job, you should mark all of the fasteners that you've torqued with a paint marker. That way you know that you've torqued them. Instructions say to set this to 5 to 6 Newton meters. I'll go ahead and set my torque wrench to 6 Newton meters. And then I'm going to do this in a consistent pattern. 1 entire row at a time so I make sure I do not miss a single attachment. Your sensor wires, you always want to start them a little ahead of where you anticipate them ending up. As you torque it down, it's hard to keep them from twisting a little bit. If you have to, you can always back it up and start it a little earlier. These PCB board screws weren't entirely tightened, so make sure and go back and check those. I do notice though that there's no board trace around them. That's something Andy complained about on his build, and they seem to have fixed it. I think in this assembly you just assume that every bolt needs checked. Alright, with the main batteries connected, let's get the BMS connections all made, and then I'll come back and make that final junction at the end. One nice thing, this new build has bus bars, flexible bus bars to everything instead of cables, so that's kind of fun. I'm going to go ahead and torque these as I go. Most of the bolts on the pre-assembled part have a paint mark on them showing that they have been, in fact, torqued and marked. However, these ones on the BMS don't have a paint mark on them, so I'm going to check them. Actually, I should check them all. and they seem to have been torqued to more than 6 Newton meters, so I think we're okay there. All right, now we want to connect these to the PCB boards. This one has some pretty good stability underneath. Now I know Andy had some issues with his wires not being seated, but mine are all good, no issues there. They seem to have fixed all the problems Andy had by this variation. Then this is our other bus. Sure it clicks on there. I double checked all of these screws that are marked, and none of them are a problem, so they came properly torqued from the supplier. This is a really nice heavy-duty breaker. I'm really happy with that upgrade, actually. Now we just need to plug in the display boards, and you really can't mess it up. They only go into one slot. Just make sure they're fully seated, but don't flex the board too hard. You don't want to break it. And then the final connection here is this cable, the power button. I don't know why we need that much wire bundled up. Find a place to zip tie all that. You know, that's one thing I've noticed with these flexible bus bars. If the bends aren't in exactly the right place, they just don't lay quite right. So while I like the bars in general, they can be a little bit of a hassle when it comes to that. And I'm just going to put some temp set screws in here so this isn't wandering all over the place while I'm setting the faceplate. Makes me nervous. Same with this guy here. Now this one has a sensor wire and the power for the BMS. The BMS is connected to the negative terminal, but it needs to be connected to the positive terminal because there's no direct connection for power. And that's what this cord is for. And I'm going to have them share this post back here. You might think, oh, you should put one under here and one under here. But remember, I want one connection that is 100% guaranteed solid to the post. That's the advantage of having two posts. And then these sensors can share a post. All right, we'll go ahead and torque these down. Now I just have one final connection to make. That's this massive bus bar that goes across the back of the battery pack. Once I make that connection, we have 52 volts available. So I wanted to do this one last. Now I should be able to get 52 volts across the whole pack. Let's see what we get. 52.7. Everything is torqued down. I've checked every fastener. All of the sensors are in place. The main bus bars are torqued down. The BMS power is connected. All right, the final piece of hardware to install is our fire suppression system. It says a sticker on the back side. Place it about the middle of the case facing out. And then it says an interesting routing system. There's one sensor here next to it. And then this one is supposed to route all the way over here. To route the sensor for the fire extinguisher, I'm going to start at this end. The sensor is supposed to be about the middle of this second bus bar. And I'll work my way around. Need new gloves. These are falling apart. There we go. Everything is done and routed. That is really, really nice. I wouldn't mind having just a piece of phenolic to set over top of that. Little insulator board would be convenient, but the lid is quite a ways above. You'd have to impact this very hard to get it to press down, but if there were an insulator board on there, it wouldn't matter if that did get damaged. It would never contact these posts. Well, that is a really nice layout. Flexible bars, double mounts, separate mount for sensor, fire extinguisher. I mean, these are very low likelihood for catching on fire, but you know, it gives you a little sense of security there to have that in there. Now I'm actually going to fire up the BMS before I put the lid on, just in case there's anything I need to access. So let's get the BMS initiated and make sure everything's working properly. All right, moment of truth. Did we set it up right? Let's see. Man, that's a nice breaker. Nice. Powered right up. I love it when things work the first time because that doesn't always happen. All right, well, everything's functioning. We have our 52 plus volts across the main terminals. The BMS power's on. We've checked the torque for everything. The fire suppressor's installed. Everything's good to go. So I can go ahead and put the lid on, fasten the rest of these screws, and then let's go through the BMS settings, get it set up, and then we'll run some capacity tests and power the house with it. Let's do it. Normally on something like this, you'd temp set them all and come back and tighten them, but the alignment is so perfect, I can just shoot them all straight in. Be nice if there were some little plugs we could put in these holes, since we don't have a battery stacked on top of it. That way you don't get dust or debris down inside there. The nice thing about this system is it uses the JK-BMS, which is a very common, popular BMS. So I can just download the app for the JK-BMS, select the one that's on the screen, And there we have it. Now I just need to go to settings, enter the password, 1, 2, 3, 4, 5, 6, verify. Then we're going to click on lithium iron phosphate. That should put in the base settings for us. We have 16 cells. Let's change the battery capacity to 314 amp hour. Oops, click OK. Let's bump the balance voltage up to 3.2. Max balance current 2 is okay. And then max continuous charge current, we want to change that to, I'm going to make that 150 amps. 40 would be way too small for what we want to do here. The rest of those I think are okay for now. Now charge, discharge, and balance are all on. You know, I think I'm going to change, let's change that to 3.3. All right, now you can see balance is off. I mean, the cells are at 50%. There's no need to be balancing at that point. It started up and man, that was easy. We just selected it, adjusted a couple settings, and we're good to go. We also have some access on the screen. We can see any alarms, the cell voltage, status of the overall battery, which is really handy. It's showing 65% right now, which is probably not too far off, but we're going to go ahead and charge it to 100%, make sure everything's balanced, run a capacity test, and then we'll do some testing with it. As I mentioned in the beginning, I ran a capacity test on these 314 amp hour cells that Yixeng sent me for this build. Here is the code for the one that I tested. They're EVE 314 amp hour MB31 lithium iron phosphate cells. And the results were fantastic. You can see from this chart, I charged the battery to 3.65 volts, let it sit for 30 minutes, then discharged it at 40 amps down to 2.5 volts. And that resulted in a capacity of 325.5 amp hours, well over the 314 amp hour rating. After the capacity test, I charged the battery back up to 3.29 volts to match the rest of the cells for our assembly. That's over 1 kilowatt hour per cell, or 16.67 kilowatt hours for this entire pack. That's more than 3 100 amp hour server rack batteries combined. Because of that overcapacity, I can use a full 15 kilowatt hours from this battery, and I don't even have to push it all the way to its limit for charge and discharge voltages. And that's going to increase the overall life of the battery pack. For our real-world test, I'm using my EG4 12K PV. I bought this from Signature Solar almost a year ago to expand my system, and I have had no issues since I installed it. It's spring, and this time of year on a sunny day, it will produce 60 kilowatt hours of energy, enough to charge 3 of these batteries. You can get a $50 discount at Signature Solar using my exclusive discount code in the description below. I've connected this battery using 2-aught cables and this ground wire I've used to bond the case to the inverter and the rest of my system. There's no need to connect the Ethernet cable in this case. There's not an official communication protocol that allows the inverter to talk to a JK-BMS. I've heard that there's been some success using the lithium setting with protocol number 6, but I didn't get it to work for me. If you know how to do it, let us know in the comments below. Either way, that's not going to be a problem because I can use the user setting mode. And these settings should be basically the same for the 12K PV or an 18K PV. I have a lot of extra cabling going on here than would actually be necessary because I wanted to include my Victron shunt within the circuit so I can monitor with a couple of different sources what's actually going on when I'm running my testing. And then the battery cables are just connected to the battery in. There's a separate breaker to turn this on and off, which is really nice. I can turn it off here at the inverter, or because we have that really nice breaker on the battery, I can turn it off there. If you want to see how to set up this inverter, I have a whole video on setting it up and doing all the settings to get it to run for an on-grid or off-grid setup. Not being able to use communication between the inverter and a battery won't be a problem because I can use the user setting mode. These settings should be basically the same whether using a 12K PV or an 18K PV. From the monitor page, I click on Maintenance, then Old Settings page, then read in the current value. If I were installing a battery with established communication, I would select lithium and the corresponding communication protocol. For any other lithium iron phosphate battery, I can use the user mode. It's labeled lead acid in the setup menu, but you can use it for any custom profile. When you click the set mode, the inverter will restart, so be prepared for that. This is a good time to talk about voltage settings. At the battery module level, we want to set the JK-BMS to the specified setting for your particular cell. I want to use the maximum charge and the minimum discharge voltage because the BMS is there to protect the battery from overcharge or over discharge, but I don't want it to interfere with my day-to-day operation at the inverter level. This chart combines the battery specs for reference with my actual settings in the inverter. The cell column is the value for an individual cell, and the battery column is just the cell column times 16, since our entire battery assembly is all the batteries in series. My tested capacity was actually 325 amp hours, so I'll enter that in the capacity line. The spec sheet calls out an end of charge voltage of 3.65 volts, which is what we set the maximum voltage in the BMS. For the battery pack, this is the absorb voltage, and I will set that to 56.2 volts, which is an equivalent of about 3.5 volts at the cell level. On the battery charging curve, you can see that this is well above the flat part of the charge curve and below the maximum setting in the BMS. Running at the extremes of the curve reduces battery life. We accomplish two things with this setting. We increase the battery life, and we keep the inverter in charge of the charge cycle. You might be concerned about not using the full capacity of the battery, but there's actually very little capacity at the tail end of the charging curve. I think you'll see when we run the test that we're able to use most of the battery capacity with these settings. And you might think, well, if lower's better, why not reduce the charge voltage even more? The problem is lithium iron phosphate has a very flat charge curve. And if you don't get above that flat line portion of the curve, the cells will never balance. And then you'll have one cell constantly getting stressed more than the others. So it's very important to have a high enough charge voltage and to hit that on a regular basis so the cells can balance out. We set the float voltage to 54 volts so that once the battery is fully charged, it won't hold it at that higher voltage or constantly run a charge cycle. That's still above the balance voltage set in the BMS, so if any cells are mismatched, the BMS can continue to balance them while it's floating. Dropping down to the charge settings, we'll be using voltage instead of state of charge, since we don't have communication. I set the charge current limit to 162 amps, which is about 0.5 C for these batteries. In my case, I have AC charge disabled, so I will only charge from solar. In backup mode, I've enabled PV charge priority and set the limit to 8 kilowatts, which is about 0.5 C for these cells. Charging faster than 0.5 C is allowed for these cells, but if we stay at or below 0.5 C, it will increase their lifespan. So in the PV charge settings, I just set my inverter max charge voltage of 56.2 volts, and we're done with charge settings. For the discharge setting, I will once again use voltage instead of state of charge. I set the charge current limit to 162 amps for this inverter, and we'll use the end of discharge voltage from our chart. I have my BMS set to the minimum at 2.5 volts, but you can see there's no real capacity left past 3 volts, so I can set the pack at a minimum of 48 volts to reduce the stress on the battery, and I'll still be able to use at least 95% of the capacity. And that's all the settings. Now that the battery is fully charged, I can enable a forced discharge from 56.2 volts down to 48 volts, and we'll see what the usable capacity range is. Since I have my battery connected through the Victron shunt, I'll have lots of monitoring capability to see how the battery performs. I ran the discharge at 4 kilowatts and it took several hours. I had some fluctuation in the charge rate as the sun was coming up. I updated the firmware and I think that's resolved the problem. Once the sun came out, it did smooth out. I stopped the test as soon as we hit 48 volts. And it probably hit that a little bit early since we were pulling 4 kilowatts at the time it hit 48 volts, but this is real world testing, right? The Victron shunt shows 305 amp hours or 15.7 kilowatt hours discharged, just shy of the 16 kilowatt hour full capacity. The BMS shows a cycle capacity a little bit higher at 311 amp hours, which is even closer to the full capacity. So with a couple different sources, you can see we'll get more than 15 kilowatt hours using these settings. And you can also see how just a slight adjustment in the max charge voltage and minimum discharge voltage will allow us to utilize 95% of the battery capacity while dramatically reducing the cycle stress on the battery. Now, just for fun, let's push the limits a little bit. If I want to charge my car, it takes about 8 kilowatts or the maximum output of this inverter. If I was using a server rack battery, I would need multiple batteries in order to achieve that level of discharge current. But this pack has a 200 amp BMS, so it should be able to support up to 10 kilowatts. To simulate the car charging, I'll set the forced discharge to 8 kilowatts, and let's see what happens. All right, the fans are howling because I have this thing maxed out at 8,000 watts. Battery says I'm pulling 167 amps. Victron shunt says I'm pulling 160 amps. We can look at this data a whole bunch of different ways. I have the EG4 app that shows we're pulling 4,000 watts from the battery and shoving that out to the grid at the moment. The BMS is going to show the highest because that's the source load, and it's at 167 amps, which is still well below its 200 amp max. And that's the most this inverter can pull. You can see the cells are all very well balanced. I can also grab my clamp meter, and it's showing 171 amps. You can even see it on the display. And it's a touch screen, so you can go through and see every cell in its situation. No alarms. And then the main status page. I really like having this display on here. Use the infrared camera here to take a look at what's getting hot. Right at the entrance here, we're getting a little bit warm. But not too bad. I have one 1/0 cable in there on my little test bench that's getting warm. Let's look inside the inverter. No significant hot spots in there. Hasn't even reached 100 degrees yet. Let's look inside the case. Make sure all our connections are good. The battery pack itself looks really good. Nothing's even reached 100 degrees in here. Everything is a nice even temperature. There's no hot spots, so that tells me everything's been properly bolted. The hottest thing in here is the bus bars, and they're barely over 100 degrees. The BMS itself, get in there on the MOSFETs, still just over 100 degrees. 113 degrees, the hottest thing I can find in there. 115. Nice. Wow. I think I'm pretty happy with that. I mean, the cable is just slightly warmer than my hand. Well, this build did not disappoint. I really like the case construction and the optional base with casters. I like the built-in breaker and the completely customizable JK-BMS with active balancing. I really like the double bolt battery connections, and whether you think it's necessary or not, I like having the fire extinguisher. As usual, I'll leave links and any discount codes that I can provide in the description below and on my website, projectswithdave.com, where you can also find all kinds of other helpful resources, calculators, and videos to help you with your solar systems. Watch this video right here if you want to see the installation for this inverter and its performance characteristics. Or if you want more on batteries, watch this video right here. Thanks for watching, and I'll see you next time.